An entire city could grow stronger from the earthquake, meant to level it. This was not fantasy, but the brilliant reality for ancient engineers who mastered nature's chaos. They did not fight against disasters like floods and volcanic eruptions. They harnessed them. By the end of this journey, you will possess a forgotten blueprint for building cities that can bend without breaking. We will uncover how Roman concrete actually gained strength from seismic shocks and why some ancient streets were designed to guide floodwaters. What do you believe it takes to build something that lasts 1,000 years? The Roman architect Vitruvius did not speak of conquering the land, but of listening to it. In his foundational texts, he insisted that a builder's first duty was a deep and patient reading of the site. This was more than a survey, it was a conversation. Where a modern planner might see a floodplain as a problem to be contained with concrete channels, these ancient engineers saw a rhythm to be respected, a force that could be guided rather than blocked. This philosophical shift from resistance to coexistence was their greatest innovation. They understood that a river's power was not malice, but physics. A seismic tremor was not an attack, but a release of energy. By accepting the inevitability of these events, they were freed to focus on intelligent design. Their goal was not to prevent the disaster, but to ensure the city could endure it. This mindset fostered incredible long-term thinking. Why build for a generation when you could build for a millennium? This reverence for natural forces was often woven into their spiritual and practical lives. Cultures around the world worshipped river deities and earth gods, a recognition of the awesome power that sustained and could destroy them. This respect was literally embedded into their urban planning, leading to cities that were not just placed on the land, but were a part of it. So what would it look like if we stopped building fortresses against nature and started building partners with it? The answer lies in the breathtakingly resilient structures they left behind, starting with a concrete that actually thrived on chaos. They understood that to survive the shaking earth, a building needed to learn how to dance. This principle of flexibility was engineered into the very ground beneath their cities. In regions shattered by frequent tremors, from ancient Greece to Turkey, builders made a revolutionary discovery. Rigid structures fought the earthquake's energy and lost, while flexible ones could move with it and endure. Their solution was not deeper or more solid foundations, but smarter ones. They began constructing multi-layered platforms of stone and rubble. Each layer was designed to shift and slide independently, so when the ground lurched, the foundation could absorb and dissipate that violent energy across its entire structure, preventing a single, catastrophic crack from traveling upwards. The Minoan Palace at Knossos on Crete stands as a breathtaking example. Its architects laid massive gypsum slabs as a base, but then they inserted long wooden beams horizontally into the stonework. Think of this not as a rigid monolith, but as a carefully crafted assembly where the timber acted as a series of shock absorbers. During a seismic event, these wooden elements would compress and flex, allowing the walls above to sway as a single, reinforced unit instead of shattering into rubble. They were building hinges into the very bones of their structures. This timber-laced masonry turned a potential collapse into a controlled, graceful movement. The survival of these palaces for millennia is a testament to its effectiveness. It was a system that protected not just the building itself, but the people living within it by ensuring the walls remained standing. How different is that from our own approach in earthquake zones today, where we often rely on immense strength to resist force, rather than clever design to redirect it? This brilliant management of horizontal force through flexible foundations finds its parallel in another ancient challenge, the control of water. While their buildings learned to dance with the earth, other civilizations were mastering a different partner, the relentless power of water. The great river cultures of Mesopotamia and the Indus Valley faced a paradox. The same annual floods that could erase their cities were the very source of their life and wealth. Their genius was not in stopping the water, but in convincing it to work for them. They designed entire landscapes as hydraulic machines. At Mohenjo-Daro, the entire city was built upon a massive, man-made platform of earth and brick, lifting it above all but the most catastrophic flood levels. But the real marvel lay below the streets, a sophisticated, city-wide drainage network of baked clay pipes and covered channels. When the rains came, this system did not just get rid of water, it managed it, directing the deluge efficiently away from homes and granaries and into designated basins or back to the river. This was proactive defense. Meanwhile, in Egypt, engineers developed the Nilometer, a simple yet profound stone structure used to measure the Nile's rise. This was their early warning system. By tracking the river's height, they could predict the coming flood's intensity. A reading that was too low meant drought and famine. One that was too high warned of destructive inundation. But a perfect reading triggered a coordinated civic response, opening diversion channels to spread the life-giving silt and water across fields, and filling massive reservoirs that would sustain the population through the dry season. Babylon took this even further, engineering intricate aqueducts and sluice gates that acted like a precision instrument for the entire river system. They could calibrate the flow, minimizing erosion and damage to the city, while maximizing the water available for their legendary hanging gardens and vast farmlands. They transformed a chaotic, destructive force into a predictable, manageable resource. This was the ultimate lesson. They stopped seeing floods as a disaster to be feared and started seeing them as a season to be harnessed. The annual threat became their most reliable asset. So what could a modern megacity, grappling with flash floods and water shortages, learn from an engineer with a simple stone gauge? It is a lesson in listening to the rhythms of the planet. But water was not the only element these masters sought to command, for some cultures looked at the raw, destructive power of fire and saw not just an end but a beginning. Even their building blocks were born of catastrophe. The Roman Empire's most enduring legacy might be a concrete that actively thrived on the very forces that should have destroyed it. While others saw the aftermath of a volcanic eruption as a barren wasteland, Roman engineers saw a treasure trove of raw materials. They discovered that the fine volcanic ash, known as pozzolana, held a secret power. When mixed with lime and rubble, it created a chemical reaction that was almost magical. This concrete did not merely resist water, it consumed it, growing stronger and more solid as it cured, even when completely submerged. The writer and architect Vitruvius meticulously documented this recipe, a mixture that could set underwater and flex under immense stress without shattering. This was the key to building on an epic scale. It allowed for the creation of the vast, unsupported dome of the Pantheon, a structure that has weathered 2,000 years of storms and tremors. It built the harbor at Caesarea with piers that stood firm against the relentless Mediterranean Sea. The very disaster that would later bury Pompeii in ash had first blessed its surroundings, enriching the soil for agriculture and providing the materials for its sturdy homes. The Romans were not just building with stone, they were building with the earth's own fiery energy, captured and transformed. This radical resourcefulness prompts a question for our own time. In an age of climate challenges, could we look to the aftermath of our own modern disasters, to wildfires or hurricanes, not just for tragedy but for new, locally sourced materials that strengthen our cities? This ingenuity with fire-forged stone finds a fascinating parallel in how other cultures learned to build with the very air itself, designing structures that could breathe with the wind. Their structures learned to breathe with the sky itself. In the vast deserts of Persia and the storm-racked coasts, architects faced an invisible and relentless force, the wind. They realized they could not build walls thick enough to stop a hurricane or a sand-laden gale, so they chose a different path to guide it, to persuade it, to turn its destructive power into a source of comfort. The entire layout of a city became a tool for aerodynamic survival. Streets were not laid out in rigid grids, but were deliberately narrow and winding. This was not chaotic planning, it was a brilliant defense. These labyrinthine passages created a natural windbreak, forcing powerful gusts to slow down, to lose their energy as they twisted and turned, dissipating their force before they could ever reach a city's heart. Outer walls were often curved, not angular, presenting a smooth, deflecting surface to the storm. Rounded corners and domed roofs became the standard, allowing the wind to flow around a building like water around a stone, eliminating the flat surfaces that would catch the full brunt of the force and be torn away. The ancient citadel of Bam in Iran is a masterclass in this philosophy. Nestled at the foot of a mountain range, its position was not accidental. The massive cliffs acted as a colossal natural shield, deflecting the region's most violent winds around the settlement. The city itself, with its organic, curved forms, worked in harmony with this natural protection. But perhaps their most beautiful innovation was the badger, or wind catcher. These towering, chimney-like structures rising from rooftops were not just decorative, they were sophisticated climate control systems. They captured the cool, prevailing breezes high above the ground and funneled them down into the heart of the home, often over a small pool of water to add moisture and cool the air further. At the same time, they created a pressure differential that sucked the hot, stale air out of the building. In a sandstorm, the design was equally genius. The carefully oriented openings could be closed or positioned to block the dust-laden winds while still allowing for ventilation. The city itself became a living, breathing organism designed to work with the air, not against it. So when we look at our own modern glass towers, which often present a flat, unforgiving face to hurricanes, we must ask, have we forgotten how to let the wind pass through? The principles that cooled ancient desert cities also held the key to surviving the cold, proving that true resilience lies in harmony with every element. The same logic of working with nature rather than fighting it extended to the very temperature of the air they breathed. In the blistering deserts of ancient Egypt and the sun-scorched American Southwest, builders faced a daily battle against the elements, with temperatures swinging from scorching heat to freezing cold in a single cycle. Their solution was not to generate more heat or more cooling, but to design buildings that acted like a thermal battery, smoothing out these extremes with quiet, passive efficiency. They constructed thick walls from adobe, a simple mixture of mud and straw. These walls possessed what we now call high thermal mass, meaning they could absorb vast amounts of heat energy during the intense daylight hours. As the sun beat down, the walls would slowly soak up that warmth, preventing it from flooding the interior spaces. Then, as the desert night grew cold, the process would reverse. The stored heat within the walls would radiate slowly back into the home, providing a gentle, natural warmth throughout the night. This created a remarkably stable and comfortable indoor climate without a single watt of electricity. The Nabateans in Petra took this concept to its most dramatic conclusion. They did not just build with stone, they carved entire cities directly into the rose-red cliff faces. The living rock itself became their insulator, a colossal thermal mass that maintained a near-constant temperature year-round, shielding inhabitants from the desert's harsh swings. Similarly, the ancestral Pueblones at Mesa Verde designed their cliff dwellings with a deep understanding of the sun's path. The massive, overhanging sandstone cliffs above them were not just shelters from rain, they were precise architectural tools. In the summer, when the sun is high, the cliff provided complete shade, blocking the direct heat. In the winter, when the sun hangs lower in the sky, its rays could slide beneath the overhang and penetrate deep into the dwellings, warming the stone walls and floors. This was a building calibrated to the movements of the solar system itself. The brilliance of these strategies lies in their elegant simplicity and their reliance on locally sourced, abundant materials. They used the earth itself to achieve perfect comfort, demonstrating that true sustainability is not about adding complex technology, but about understanding the inherent properties of the world around us. What could our own architecture achieve if it were designed first and foremost as a responsive partner to its local climate, rather than a sealed box reliant on constant, artificial energy? This mastery of temperature created stable homes, but a stable home is useless if the ground it stands on is washing away. They turned mountainsides into living, breathing architecture. Across the steep slopes of the Andes, Inca engineers faced a constant and devastating threat, not from a sudden quake or flood, but from the slow, creeping disaster of erosion. Every heavy rain threatened to wash the lifeblood of their civilization, the soil itself, down the barren hills and into the rivers below. Their solution was a masterpiece of landscape engineering, the vast stair-step terraces that still define the region today. These were not just flat spaces for crops, they were a complex system for controlling the very flow of the earth. Each terrace was a massive retaining wall, built with stones so precisely cut and fitted that they locked together without any mortar. This precision was not for aesthetics, it was pure function. The tight joints allowed rainwater to seep through the wall slowly and evenly, instead of building up pressure and bursting through in a destructive cascade. This slow drainage prevented the soil behind the wall from becoming waterlogged and sliding away in a catastrophic landslide. The terraces transformed a steep, unstable slope into a series of gentle, manageable steps, taming the force of gravity itself. Spanish chroniclers who first witnessed Machu Picchu centuries after its abandonment wrote with astonishment of these structures, still perfectly intact after generations of torrential rains that would have scoured a natural hillside down to bare rock. But the stonework was only half of the genius. The Incas integrated the local ecosystem directly into their design. They planted native grasses and shrubs along the edges of the terraces and within the soil. The dense, matted root systems of these plants acted as a living net, binding the soil particles together and creating a resilient mat that further resisted the erosive power of running water. This combination of intelligent stonework and strategic vegetation turned a potential wasteland into a fertile, productive garden that also protected the city below from mudslides and destabilization. They did not conquer the mountain, they collaborated with it, weaving their agriculture and their architecture directly into its contours. How many modern construction projects, which so often begin by clear-cutting and flattening a site, could learn from this ancient wisdom? What if our cities saw green spaces not just as decoration, but as vital, structural components that hold the ground together? This deep-rooted harmony with the landscape reveals a blueprint for surviving almost any natural force, even the raw, untamed power of the sky itself. They even found a way to harness the fury of the sky. While we often credit Benjamin Franklin with the invention of the lightning rod, ancient builders displayed a remarkable, intuitive understanding of electrical dangers long before the principles were formally defined. In an age where a single lightning strike could reduce a wooden temple or a thatched palace to ashes, they developed clever, preemptive defenses. High atop sacred structures in ancient Greece and Egypt, builders often installed gleaming pinnacles of gold or bronze. While their primary purpose may have been spiritual or decorative, these metallic caps served a profound practical function. Observant engineers likely noticed over generations that lightning, a seemingly divine and unpredictable force, was consistently drawn to these shining points. By intentionally placing conductive metal on the highest peaks and then physically connecting it to the ground via metal strips or rods, they created a controlled pathway. This system would attract a bolt and then channel its immense energy safely down into the earth, away from the flammable building materials below. The Great Lighthouse of Alexandria presents a fascinating case. Its legendary polished bronze mirror, designed to reflect a beacon of fire for ships far at sea, was mounted at the very summit of the colossal structure. Many experts now speculate this massive metal assembly would have acted as a giant lightning rod, naturally intercepting strikes that would otherwise have set the towering wooden interior ablaze. This was not a matter of fighting the storm, but of giving its power a preferred exit route. It was a brilliant, risk-mitigating design that turned a catastrophic threat into a manageable event. How many of our own skyscrapers, bristling with sensitive electronics, could benefit from such elegantly simple and redundant protective systems? This clever management of a sudden, fiery strike from above finds its perfect counterpart in how they dealt with a far slower, more insidious threat, the silent, creeping danger of sediment that could choke a city from below. They turned a river's choking breath into its lifeblood. For the great civilizations along the Nile and the Yellow River, the annual flood brought more than just water. It carried immense volumes of silt. This rich sediment was the source of their agricultural wealth, but left unchecked, it was also a slow-moving urban killer. If allowed to accumulate, silt would clog the intricate networks of canals, block harbor entrances, and elevate riverbeds until the very waterways designed to control flooding became the cause of it. Their genius was in managing this constant, creeping flow of earth. They did not try to stop the silt from coming, they orchestrated where it would go. In ancient China, meticulous records detail vast irrigation networks that were more than just water channels. They were sophisticated sorting systems. Engineers designed primary canals with gentle, calculated gradients. As the silt-laden water entered these channels, its speed would naturally slow, allowing the heavier sand and silt particles to settle out in wide, specially constructed basins before the clearer water continued onto the cities and harbors. This captured silt was not waste, it was a resource. Laborers, often employing seasonal workforces mobilized during the dry period, would then dredge these basins and transport the nutrient-rich sediment directly to the fields, manually completing the cycle that nature had begun. The city of Thebes in Egypt perfected a similar rhythm. Its system of canals and water gates was designed for adjustment. These were not static structures but dynamic tools. Workers would regularly clear the channels, and strategically operated gates could be used to divert the most sediment-heavy water at the peak of the inundation away from critical infrastructure and toward vast agricultural floodplains. This was a continuous, active partnership with the river. They were not building a permanent solution, but a maintainable one. The system acknowledged that the river would always bring the silt, so the city's task was to always be ready to receive it and redirect it. This proactive maintenance transformed a looming disaster of clogged waterways and stagnant floods into a guaranteed agricultural bounty that could support immense, dense urban populations. How many of our own modern rivers, choked by sediment behind massive, static dams, could be revived by such dynamic and cyclical management? This brilliant control of sediment relied on something far more subtle than engineering alone. It required an intimate understanding of nature's own timetable. Some societies built not for permanence but for dynamic change. For the nomadic cultures of Central Asia, a city was not a fixed point on a map but a living entity that could walk away from danger. Their greatest innovation was an architecture of motion, designing entire settlements with seasonal disaster risks woven directly into the blueprint. When faced with predictable spring floods or punishing droughts, they did not build higher walls or deeper wells, they built lighter structures. Palaces described by Mongol historians were not stone fortresses but vast, magnificent complexes of felt and wood, engineered to be disassembled in days and loaded onto carts. Their bridges were not fixed stone arches but clever, modular assemblies that could be taken apart before the river ice melted, avoiding destruction by the very water they crossed. This was not a retreat from nature, but a graceful dance with its cycles. Their secret weapon was a profound literacy in the language of the land. They read environmental cues like a daily forecast, watching the patterns of animal migrations for signs of shifting weather, or monitoring the subtle rise of river levels long before the flood arrived. This constant observation allowed for a proactive, not reactive, response. We see a parallel philosophy in the ancient Amazon, where communities built entire villages on towering stilts. When the annual rains came, the water would simply flow beneath their homes, their lives elevated above the temporary deluge. This embrace of flexibility fundamentally reduced their vulnerability. They invested not in immovable assets, but in portable wealth and resilient social structures that could maintain cultural continuity even as their physical location shifted. So what would it take for a modern coastal city to incorporate such adaptive thinking? Instead of just building permanent seawalls, could we design critical infrastructure like power stations or emergency housing to be modular and temporarily relocated ahead of a predicted storm surge? This ancient reliance on environmental cues reveals the most powerful early warning system of all, a community deeply connected to its surroundings. Their most sophisticated warning system was not built of stone but of shared knowledge. Long before the first tremor or flood surge, ancient societies were already receiving signals, reading a language written in the behavior of animals and the patterns of the sky. They understood that nature itself provides the earliest alerts for those who know how to listen. In regions plagued by earthquakes, generations of observation revealed that animals often behave strangely hours or even days before a major seismic event. Dogs would bark incessantly, rodents would flee their burrows, and birds would fall silent. These were not seen as random omens, but as reliable indicators of subtle changes in the Earth's electromagnetic field or the release of gases that animals could perceive. This communal knowledge was formalized into a system of vigilance. Lookout towers were strategically placed along coastlines and mountain passes, manned by designated observers trained to spot the specific cloud formations that preceded violent storms or the sudden, unnatural retreat of the ocean that signaled an approaching tsunami. In the Pacific Islands, elders taught younger generations to read the ocean's subtle shifts, the arrival of certain deep water birds inland, and the peculiar quality of the waves, allowing entire villages to evacuate to higher ground long before the wall of water appeared on the horizon. The ancient Maya constructed towering temples that served a dual purpose. Their heights were not just for reaching toward the gods, but for observing the horizon. Priests and astronomers would track celestial events and weather patterns from these vantage points, integrating astrological cycles with practical disaster management to predict seasonal hurricanes and droughts. When a threat was identified, the response was swift and coordinated. Messages were relayed across vast distances using a network of signal fires, the resonant beat of drums or teams of highly trained runners. This created a web of awareness that could alert an entire region in a matter of hours. The true power of this system lay in its collective nature. By empowering every member of the community to recognize a few key signs, and by having a clear, practiced chain of communication, they transformed individual observation into a city-wide shield. This shared responsibility drastically reduced panic because everyone knew the plan. So how can we, with all our satellites and sensors, learn from this? What if our modern emergency alerts were supplemented by community training programs that teach people to read the local environment, creating 1 million human sensors embedded in every neighborhood? This deep awareness provided the time to react, but true resilience also demanded structures that could be repaired or replaced with astonishing speed. Their buildings were designed to heal. In the earthquake-prone landscapes of ancient Japan, the goal was not to create a structure so strong it would never break, but one that could be fixed with astonishing speed. The traditional wooden frame house with its paper-thin walls was a masterpiece of repairability. Its strength came from an intricate skeleton of interlocking wooden joints, techniques refined over centuries. These joints were not nailed or glued rigidly together. They were carefully carved to fit like a three-dimensional puzzle, allowing the entire frame to sway and flex during a tremor. The walls themselves, made of lightweight paper and thin wood, were not load-bearing. When the earth shook, these panels would break first, acting as a sacrificial element. They were the crumple zone of the ancient world, shattering to absorb energy and protect the crucial wooden frame from catastrophic failure. After the shaking stopped, the community could simply replace the broken panels with new, standardized ones, often within days. The core structure remained intact, and life could resume with minimal disruption. This philosophy of modularity reached its most profound expression at the Eye's Grand Shrine, one of Japan's most sacred sites. For over 1,300 years, this shrine has been ritually demolished and rebuilt on an adjacent site every 20 years. This practice, known as Shikinen Sengu, is far more than a religious ceremony. It is a living repository of architectural knowledge. Each generation of craftsmen must relearn the exact modular plans and complex joinery techniques, ensuring that the skills to build and, more importantly, to repair are never lost. The shrine is not an aging relic, it is perpetually new, its design continuously validated and subtly improved with every cycle. This creates a culture where repair is not a sign of failure, but an expected and celebrated part of a building's life. In the ancient city of Kyoto, this principle was woven into daily life. Sliding interior walls and partitions meant that the internal layout of a home could be easily altered, and damaged sections swapped out without touching the fundamental structure. A family's home could weather a quake and be made whole again before the next harvest. This approach prioritized community stability over the illusion of permanent, unbreakable buildings. It reduced long-term economic hardship and embodied a truly sustainable practice, using renewable materials in a cycle of use and renewal. So what would it take for our own urban housing to embrace such modularity? Could we design apartment blocks where entire wall units or facade panels are standardized and easily replaceable after a storm or quake, turning a months-long reconstruction into a weeks-long repair job? This brilliant focus on the surface and the skeleton, however, was only possible because of a much deeper understanding, one that reached far below the foundations and into the very bones of the earth. The ground itself became their strongest ally. Ancient engineers understood that the most resilient structure could still fail if it was built in the wrong place, which is why their first and most critical step was a deep geological reading of the land. They did not simply claim a plot of flat ground, they sought out stable foundations, deliberately avoiding the hidden dangers of active fault lines and unstable, sliding slopes. Instead, they leveraged the immense strength of natural rock formations, using them as a living platform for their cities. The citadel of Mycenae in Greece stands as a powerful testament to this principle. It was not placed on the convenient plain below, but perched high upon a rugged, rocky outcrop. This was not just for defense against armies, it was a masterstroke of geological site selection. The solid limestone bedrock provided a foundation immune to erosion and liquefaction during earthquakes, while the hill's natural contours were expertly harnessed to create a gravity-fed drainage system that whisked rainwater away, eliminating the risk of landslides and destructive flash floods at the city's gates. This knowledge was not guesswork. Builders consulted with what we would now call geologists, as well as tribal elders who held generations of observational data. They learned to read the landscape like a book, identifying safe zones by the presence of specific, deep-rooted vegetation or by the feel of the soil underfoot. In Mesoamerica, the builders of Teotihuacan aligned their entire metropolis, including the vast Avenue of the Dead with the surrounding mountain peaks. This alignment held profound spiritual meaning, but it was also brilliantly practical. The massive mountain range acted as a colossal natural windbreak, diverting powerful storm winds around the city, and its foothills channeled seasonal rainwater along predetermined paths away from the urban center. They were not building on the land, but with it, embedding their settlements into the very bones of the earth for added protection. How many of our modern suburbs, sprawling across floodplains and unstable hillsides, ignore this fundamental wisdom? The enduring legacy of these cities challenges us to see a building site not as a blank slate to be conquered, but as a partner with its own strengths and warnings. This profound integration with the geological landscape was often guided by another layer of ancient genius, a hidden language of sacred geometry that governed their most stable designs. Their buildings were not just structures, they were mathematical poems written in stone. Across the ancient world, from the temples of Greece to the stepwells of India, master builders integrated a hidden language of sacred geometry into their designs. They believed that certain mathematical ratios, like the famous golden ratio, were not merely aesthetically pleasing, but held the key to profound structural resilience. This was the principle of proportional harmony, an engineering philosophy where beauty and brute strength were one and the same. The Parthenon stands as the ultimate testament to this idea. Its facade is a masterclass in the application of the golden ratio, a proportion where the relationship between the whole and its parts is perfectly balanced. But this was far more than an artistic choice. Modern analysis suggests that this specific geometry helped distribute the immense physical stresses of wind and seismic, shaking evenly across the entire structure. By eliminating sharp, weak points and creating a more organic, flowing form, the building could dissipate vibrational energy, swaying as a unified whole rather than cracking apart at its joints. It was architecture that worked with the physics of force, not against it. This wisdom was echoed halfway across the world in the Indian science of Vastu Shastra. Here, the entire layout of a city or a home was planned according to cosmic diagrams called mandalas. These intricate geometric patterns dictated the placement of walls, doors, and columns, all oriented to promote balance and durability. A building designed under these principles was believed to be in harmony with the natural energies of the earth, resulting in a space that was not only spiritually serene but also remarkably sturdy. The stepwells of Gujarat, with their impossibly precise, repeating geometric patterns carved deep into the earth, have survived centuries of monsoon rains and minor tremors, their stability a direct result of their proportional perfection. Could our modern glass and steel boxes, so often designed with cost efficiency as the primary driver, learn from this ancient marriage of math and material? The answer lies not just in the blueprint, but in the very substance these geometric forms were built from, leading to one of history's most ingenious composite innovations. They even mixed their mortar with breakfast, while the Romans perfected their volcanic concrete on the other side of the world. Chinese engineers discovered a culinary secret to immortality for their structures. They developed a revolutionary composite by blending standard lime mortar with a simple, sticky soup made from boiled rice. This sticky rice mortar was not just an adhesive, it was a chemical marvel. The amylopectin molecules in the rice acted as an organic binder, creating a microstructure that was incredibly dense, waterproof, and far more flexible than traditional lime. When used in the foundational sections of the Great Wall, this composite did not simply hold stones together. It created a unified, monolithic structure that could sway with seismic tremors without fracturing. The mortar was so resilient that weeds and roots could not penetrate it, preventing the biological erosion that crumbles so many ancient ruins. This was not a single, isolated recipe, but a widespread principle of composite innovation. Builders became material scientists, constantly testing local resources to create custom blends. In the flood-prone regions of ancient Peru, engineers faced the constant threat of heavy rains dissolving their earthen adobe bricks. Their solution was as ingenious as it was simple. They extracted the viscous sap from the prickly pear cactus and mixed it directly into the clay. The long, fibrous polymers in the cactus juice acted as a natural waterproofing agent, binding the clay particles together and creating a surface that shed water like a duck's back. Similarly, from the Middle East to Africa, builders routinely added chopped straw to their mud bricks. This was not just filler. The straw fibers provided crucial tensile strength, much like the rebar inside modern concrete, preventing the bricks from cracking apart as they dried and settled. These ancient composites achieved something pure stone or clay could not. They were multifunctional. A single material could now be waterproof, flexible, and strong, all by intelligently combining the humble resources at hand. So what modern composites could we develop if we look to our own local, natural world for inspiration? Could we invent a polymer reinforced with agricultural waste, or a building insulation grown from fungus? This ancient mastery of material blends finds its ultimate expression in the forms these composites were shaped into, the timeless strength of the arch and the dome. They mastered the strength of the curve. Roman and Persian architects discovered that a straight line was often the weakest shape when facing nature's immense pressures. By perfecting the arch and the dome, they engineered structures that could redirect crushing weight and violent seismic forces along graceful, continuous pathways. This was not about creating thicker walls, but about designing smarter shapes. A curved form naturally channels stress downward and outward along its entire surface, eliminating the sharp, weak corners and flat spans that are prone to collapse under a heavy load of snow or the sideways lurch of an earthquake. This principle allowed them to create vast, open interiors, spaces that felt both majestic and secure, because they were free from the forest of internal columns that would have been necessary with a simpler, rectilinear design. The breathtaking Hagia Sophia in Istanbul stands as the ultimate testament to this genius. Its colossal dome seems to float weightlessly above a square base, a miracle made possible by the revolutionary use of curved triangular supports known as pendentives. These pendentives act as a transitional skeleton, gracefully transferring the dome's immense weight down to four massive piers, while also allowing the entire structure a degree of flexible movement during seismic events. The building breathes with the Earth's tremors. This incredible stability relied on absolute precision. Each stone in an arch or vault was meticulously cut, its shape and angle calculated to perfection. When locked into place with a strong mortar, these stones became a single, self-supporting unit, where each block leaned on its neighbor, held in a perfect state of compression. The ancient Roman aqueducts, marching across valleys on endless sequences of these stone arches, demonstrate the principle on an epic scale. If the ground shifted slightly beneath one arch, the repetitive, modular design ensured the entire structure could flex and settle without a catastrophic failure, keeping the life-giving water flowing for centuries. So how can contemporary architects relearn this ancient wisdom? In an age of boxy skyscrapers, could the reintroduction of arched forms and domed roofs in our schools, hospitals, and public spaces create buildings that are inherently more resilient to both quakes and extreme weather? The enduring power of these curved forms shows that sometimes the strongest path is not a straight line, but a perfectly calculated arc. Yet, the most resilient designs often understood that what you leave out is just as important as what you put in. They designed their cities with empty pockets, knowing that the strongest defense was sometimes a planned absence. This principle of strategic voids transformed potential disaster zones into resilient landscapes. In flood-prone regions, ancient engineers did not just build barriers, they carved out spaces specifically meant to be filled with water. They incorporated vast open plazas, sunken gardens, and even subterranean chambers that served as giant sponges during an inundation. When the waters rose, these voids absorbed the immense volume, drastically reducing the hydraulic pressure on surrounding buildings and critical infrastructure. The Aztec capital of Tenochtitlan, built upon Lake Texcoco, was a masterwork of this philosophy. The city was not a solid mass of land, but a network of canals and artificial islands called chinampas, or floating gardens. These waterways and cultivated plots were not merely for transport or agriculture, they were dynamic buffer zones. During the intense rainy seasons, the canals would expand, their capacity to hold water increasing naturally. Historical accounts describe how these pre-planned voids would temporarily store the deluge, holding the water safely within the city's fabric until it could be gradually released back into the lake system or used for irrigation. This was not just drainage, it was a sophisticated form of urban hydrology. Across Southeast Asia, this same logic was applied on a domestic scale. Entire villages were constructed on stilts, elevating the living quarters high above the ground. The space beneath the homes was not wasted, it was a designated overflow channel. When the annual monsoon floods arrived, the water would simply flow through this void, passing harmlessly underneath the community without applying destructive force to the structures themselves. Life continued above the temporary river. By intentionally planning for emptiness, these societies fundamentally changed their relationship with flooding. They stopped seeing water as an invader to be repelled and started treating it as a guest with a pre-arranged place to stay. This proactive design turned catastrophic events into manageable, seasonal cycles. What role could such strategic emptiness play in our own modern, paved-over cities where every square inch is built upon and rainwater has nowhere to go but into overwhelmed sewers? Managing the pressure of water was a monumental task, but these same engineers also had to contend with a faster, more furious element, fire. Fire was the ancient city's silent partner in chaos, a threat that could ignite from a single lightning strike or a cooking hearth and erase entire neighborhoods in hours. After experiencing devastating blazes, civilizations like Rome did not just react. They redesigned their urban fabric to starve the flames before they could even begin. They engineered wide, stone-paved streets that acted as natural fire breaks, creating impassable gaps that halted a fire's advance through densely packed districts. Emperor Augustus established history's first dedicated firefighting corps, the Vigiles, but his true genius was in prevention. He championed the use of marble and stone for public buildings and enforced zoning laws that physically separated risky industrial workshops like blacksmiths and potters from residential areas. This strategic separation meant a spark from a forge would not find a path of wooden shingles leading to a city-wide inferno. They integrated water security directly into the plan, ensuring that public fountains, reservoirs, and aqueducts were never far from any neighborhood, providing the Vigiles with the tools they needed at the source. In Japan, the lesson was learned with equal force. Castle towns mandated plastered walls and heavy tile roofs, materials that would not catch a single ember carried on the wind. The defensive moats that surrounded these settlements served a dual purpose. They were both a barrier against armies and a ready-made reservoir for fire suppression crews. This was not a single solution, but a layered system of defense woven into the city's very blueprint. The open plazas and forums of Rome were not just social spaces, they were pre-planned voids of safety, places where fleeing citizens could gather and where the fire would find no fuel. So how can a modern metropolis with its own dense tangle of materials and energy lines apply this ancient wisdom? Could we reintroduce strategic greenways and non-combustible building zones not as afterthoughts, but as integral parts of our urban DNA, creating a city that is inherently fire-resistant? This brilliant containment of fire secured the structures, but a city is more than its buildings. It is its people, and their survival depended on a more fundamental resource, a secure food supply when everything else had fallen apart. Their survival blueprint included a hidden network of larders and reservoirs. When a single drought or raid could erase a city's future, ancient engineers did not rely on one central granary or a solitary well. They built redundancy into their very supply lines, creating multiple, dispersed caches of food and water that acted as a collective insurance policy for the entire community. The ancestral pueblones of the American Southwest perfected this strategy in the arid landscapes of Choco Canyon. They constructed granaries high up on sheer cliff faces, tucked into natural alcoves. These were not random hiding spots, but strategically chosen locations that were difficult for rivals to access, yet formed an interconnected web of supply nodes across the region. The storage chambers themselves were engineering marvels, designed to preserve their precious contents for years. They were carved into the rock or built with thick, insulating adobe bricks that maintained a cool, stable temperature, protecting seeds and dried goods from spoilage in the desert heat. Their water systems were equally sophisticated. Across the canyon, they engineered vast networks of channels and basins carved directly into the rock, designed to capture every precious drop of rainfall. These systems would funnel water from a wide catchment area into carefully positioned reservoirs, some lined with clay to prevent seepage. This was not a passive hope for rain. It was an active harvesting of every possible ounce of moisture, stored in multiple, redundant locations so that if one reservoir failed or was contaminated, others would still support the population. This philosophy of over-preparation was a cultural cornerstone. Communities would deliberately stockpile a surplus far beyond their immediate needs, creating a buffer for the inevitable lean years. The ancient Nabateans in Petra demonstrated this with breathtaking ingenuity. Their city, carved into rose-red cliffs, was surrounded by desert. Their survival depended on capturing flash floods. They engineered a complex system of dams, tunnels, and channels to control these sudden torrents, but their true genius lay in storage. They carved immense, waterproof cisterns directly into the solid rock beneath the city. These were not open pools vulnerable to evaporation and contamination, but sealed, subterranean vaults that kept water cool and fresh for months, even through the longest dry spells. This decentralized, redundant storage did more than just prevent starvation. It promoted profound social stability. When a disaster struck, whether a drought or a conflict, the community did not fracture in a desperate scramble for the last remaining resources. The knowledge that there were multiple known backup supplies prevented panic and fostered a sense of collective security. The entire city became more resilient because its lifeblood was not concentrated in a single, vulnerable heart, but pulsed through a distributed network. So what would it take for a modern megacity to adopt this ancient wisdom? Instead of relying on a few centralized water treatment plants and massive, singular grain silos, could we design neighborhoods with their own local, secure water catchments and food storage hubs, creating an urban fabric that can withstand a shock to any one part of its system? This distributed safety net for physical survival was only half of the equation, for a city also needs to maintain its nervous system, the flow of information when everything else is falling apart. Their communication networks were the nervous system of the ancient world, a web of light and sound that could alert an empire in a single night. When a disaster struck or a threat loomed, the speed of information was their greatest shield. The Roman Empire's legendary road system was far more than a path for legions. It was a high-speed information highway. Couriers stationed at relay posts a day's ride apart could carry messages from one end of the Mediterranean to the other in a matter of weeks, an astonishing feat for the ancient world. But for true emergencies, they employed something faster than any horse, the beacon chain. Watchtowers were strategically placed on high ground, each within clear sight of the next. A single fire lit at a distant outpost would be seen and replicated by the next tower, and the next, creating a wave of light that raced across the countryside at the speed of sight. A coordinated attack, a volcanic eruption seen from afar, or news of a river flooding its banks could be signaled to the capital long before any physical report could arrive. This system was brilliantly redundant. If one tower fell or was obscured by weather, messengers on horseback from adjacent stations would carry the word along the road, ensuring the message found another path. The Inca perfected this with their own breathtaking infrastructure. Their empire sprawled across some of the most rugged terrain on Earth, yet their network of runners, using suspension bridges and stone-paved trails that clung to mountain cliffs, could relay a message from the capital to the coast in just a few days. They may have even used the quipu, that complex system of knotted cords, to encode disaster data, perhaps quantifying the number of people displaced by a landslide or the volume of grain needed for relief, allowing for a coordinated, data-driven response from the central government. In ancient China, the Great Wall's watchtowers served a dual purpose. They were defensive positions, yes, but their primary function was communication. A specific sequence of smoke signals by day or fire beacons by night could convey not just the simple fact of an attack, but the size and direction of an invading force, or even the outbreak of a wildfire or flood in a distant province. This allowed the empire to marshal resources and direct aid with a precision we would admire today. So how fragile are our own digital networks, which can be silenced by a single downed power line or a cyber attack? The lesson is not to abandon technology, but to weave it together with low-tech, resilient backups, creating a communication system that cannot be so easily broken. This physical network of signals was often powered by something less tangible, a shared spiritual belief that the community's survival was a sacred duty. Their spiritual beliefs were a shield for the mind, a form of psychological engineering as vital as any stone wall. ancient societies understood that a city's resilience depended not just on its physical defenses, but on the unshakable spirit of its people. They wove this understanding directly into their cultural fabric, using myth and ritual to transform the terror of natural disasters into a narrative of renewal. In Mesopotamia, the Epic of Gilgamesh was far more than a story. It was a cultural anchor. Its great flood narrative did not end with annihilation, but with a new beginning, a world washed clean and ready for rebirth. Hearing this tale recited generation after generation instilled a profound lesson. Destruction was not a final end, but a phase in a great repeating cycle. This cultural memory fostered a mindset of acceptance and hope that was crucial when the real Tigris or Euphrates rivers overflowed their banks. Instead of succumbing to despair, the community saw the floodwaters as a difficult but necessary step toward future fertility, a trial they were prepared to overcome because their very identity was built around this cycle. In Egypt, this principle reached its zenith with the annual inundation of the Nile. Rather than dread the rising waters, they celebrated the arrival of the flood with the festival of Wepet Renpet, the opening of the year. This was a time of music, feasting, and offerings to the god Hapi, who embodied the life-giving flood. By turning a potential crisis into the central event of their calendar, they accomplished something brilliant. They normalized the disaster, reducing the collective panic and unifying the entire population in a shared, proactive response. Everyone knew their role, from the priests reading the nilometers to the farmers preparing their fields for the rich silt. The disaster became a communal project, not a chaotic emergency. This integration of spirituality and practicality provided a profound sense of control in the face of uncontrollable forces. It supported mental and emotional well-being by giving people a framework to understand their suffering and a shared purpose to move beyond it. Their rituals were a form of collective therapy, reinforcing social bonds and a collective identity that proved unbreakable during a crisis. So how can our modern, often secular, disaster management plans incorporate this kind of cultural and psychological support? Could community drills be paired with local festivals, or could rebuilding efforts be framed as a collective renewal, a modern-day epic of perseverance? This deep-seated mental resilience was a city's soul, but its body also required a robust economic foundation to recover. Their wealth was designed to survive the storm. When a natural disaster struck an ancient city, it was not just the walls that needed to hold, but the economy itself. Societies like Carthage and Athens understood this deeply. They did not store all their prosperity in one form or one place. Instead, they built economic systems with multiple layers of protection, ensuring that a single catastrophe could not erase their financial foundation. They stored vast reserves of wealth in durable, universally valued forms like gold and silver, metals that could survive a fire, a flood, or an earthquake, and be used immediately to fund recovery. But their genius went beyond mere treasure hoards. The Phoenician traders, masters of the Mediterranean, pioneered a form of risk management that feels strikingly modern. They never relied on a single port or a single trade route. Their commercial networks were a sprawling web, connecting cities from Tyre to Carthage to Cadiz. If a tsunami destroyed one harbor or a war closed another, their ships could simply redirect to a dozen other friendly ports. The loss of one node in their network was a setback, not a collapse. This diversification was their financial shock absorber. We see a parallel strategy along the Silk Road. A landlocked city in Central Asia did not depend solely on the caravan traffic from the east or the west. It fostered local industries from metalworking to textile production that were insulated from the droughts or bandit raids that might plague a distant stretch of the trade route. Their economy was a mixed portfolio, so a shock to one sector would not trigger a total downfall. Perhaps their most profound innovation was an early form of community insurance. Historical records describe how traders and citizens would pool resources into a common fund. When a merchant ship was lost at sea or a farmer's fields were salted by a storm surge, this collective treasury would provide loans or outright grants to help them rebuild. This system distributed the immense cost of a disaster across the entire community, preventing any single family or business from being ruined and dragging the local economy down with them. It was a social safety net woven from mutual interest. So what can a modern metropolis, whose economy might be tied to a single industry or a fragile global supply chain, learn from this? Could we incentivize local business diversification and create community-funded resilience loans to help small businesses recover after a hurricane or wildfire? This financial foresight provided the means to rebuild, but it was meaningless without a vision that stretched across generations. They built for the grandchildren they would never meet. This was the essence of true long-term urban planning, a vision that stretched across centuries, not just political terms. In the shadows of the rising pyramids, Egyptian engineers were not just stacking stones, they were executing master plans that spanned the entire reign of a pharaoh and beyond. Each phase of construction was meticulously documented and passed down, with apprentices learning not only how to place a block, but why it was placed at that specific angle to deflect the abrasive desert winds, or how the internal passageways were engineered to shift minutely without collapsing under their own weight over 1,000 years. This was succession planning on a civilizational scale. The knowledge of how to maintain canals, repair dikes, and read the Nile's mood was not left to chance. It was embedded into the priesthood and the scribble class through a rigorous system of apprenticeship, ensuring that the administrative and engineering memory of the state outlasted any single individual. In Mesopotamia, the same profound foresight was etched into clay tablets. These were not just royal boasts, but practical manuals detailing the maintenance schedules for city walls and the specific protocols for mobilizing labor when the Euphrates threatened to overflow. The famous Code of Hammurabi included laws governing builders' responsibilities, creating a legal framework for durable construction that held craftsmen accountable for their work for years after its completion. This institutional memory transformed disaster response from a panicked reaction into a well-rehearsed civic drill. Perhaps no text captures this holistic, long-term view better than the Arthashastra from ancient India. This comprehensive treatise on statecraft dedicated entire chapters to the administration of cities, specifying everything from the ideal width of streets to the maintenance of public granaries and the precise emergency protocols for fires and floods. It mandated that city planners set aside space for future expansion and for gardens that could serve as fire breaks and flood zones, acknowledging that a city is a living entity that must be allowed to grow and adapt. This multi-generational perspective was their ultimate innovation. They understood that a city's resilience was not a one-time achievement, but a continuous process that had to be nurtured across generations. So what would it mean for a modern mayor to think like an Egyptian vizier, approving infrastructure projects with a 200-year lifespan, or for a city council to establish a permanent fund for maintenance, untouchable by short-term budget cycles? This deep time horizon ensured that the blueprint for survival was never lost, but was instead carefully preserved and handed down, a sacred trust between the past and the future. Their stories were their sturdiest libraries. Before a single stone was laid, ancient societies understood that the most resilient structure of all was the one built in the collective memory of the people. They encoded their hard-won engineering wisdom not just in stone, but in song, story, and meticulous manuals, creating a knowledge bank that could survive the total destruction of the physical city. The epic poems and oral histories passed down around campfires were far more than entertainment. They were vital survival guides. For generations, Native American tribes living along the Mississippi preserved detailed flood narratives. These stories, rich with symbolism, also contained precise, practical data. They recounted which hills served as the highest safe ground, which forest trails remained passable during a deluge, and how to read the river's mood days before the waters crested. This was actionable intelligence, woven into the cultural fabric so it could never be lost or forgotten. Similarly, the detailed architectural texts of figures like the Roman engineer Vitruvius became the bedrock of Western building science. His multi-volume work, De Architectura, was a comprehensive manual covering everything from selecting stable ground to mixing the perfect volcanic ash concrete. He did not just state what worked, he explained the underlying principles of why it worked, ensuring that future builders could adapt the knowledge to new materials and new challenges. This created a powerful redundancy. A master stonemason would train multiple apprentices in the exact same techniques of complex joinery or foundation laying. If one craftsman was lost, the knowledge lived on in several others. The community itself became the backup hard drive. In ancient India, the intricate rules of Vastu Shastra were transmitted through a rigorous oral tradition from teacher to student, repeated and debated until they were second nature. This ensured that the geometric principles for stable, harmonious construction were deeply ingrained and could be replicated even if every written text was destroyed. So how do we, in our digital age, protect our own critical knowledge from a power outage, a server failure, or simple obsolescence? Could we pair our cloud storage with community story circles, where local disaster responses are taught not as dry manuals, but as engaging narratives for the next generation? This profound commitment to preserving wisdom ensured that solutions could be rediscovered, but the ultimate test of resilience was a city's ability to learn from the ruins themselves. Their ruins became the very bedrock for a new beginning. When an earthquake shattered a city or a flood scattered its stones, ancient engineers saw not just a tragedy, but a sudden, massive quarry of pre-processed materials. They pioneered the adaptive reuse of disaster-damaged components, turning rubble into resilience. At the archaeological site of Troy, the layers of the city tell this story of cyclical renewal. One level of the city, destroyed by fire or conquest, was not simply cleared away. Its fallen stones, many still solid and square, were carefully sorted and lifted to form the foundations and walls of the next incarnation of Troy. This was not a haphazard patchwork, but a deliberate engineering strategy. Builders would assess each cracked column and splintered beam, judging which pieces could bear weight again and which should be crushed for a new, stronger mortar. This process drastically accelerated rebuilding, allowing a community to restore its protective walls and essential structures in a fraction of the time it would take to quarry and transport all new stone. It was a practical response that also conserved vital resources, turning a liability into an immediate asset. In ancient Jerusalem, this philosophy was etched into the city's soul. When the first temple fell, its monumental stones were not discarded as symbols of defeat. Instead, they were respectfully and strategically repurposed, integrated into the defensive walls that would protect the city's future. These recycled stones carried the weight of history, literally building resilience from the memory of past destruction. The technique required a deep understanding of material science. A stone cracked by an earthquake's shear force might not be suitable for a foundational plinth, but it could be perfectly sound when rotated and set as a header stone in a wall, where the pressure would be distributed differently. Timber beams, charred on the outside but structurally sound within, could be planed down and reused, their fibers now hardened by fire. This was sustainability born of necessity, a circular economy that minimized waste and maximized the utility of every available resource. So what would it take for our own construction industries, which generate mountains of demolition waste, to look at a collapsed building not as a clean-up site, but as a source of salvaged, high-strength materials? This brilliant recycling of the past provided the physical means for rapid recovery, but the speed of that recovery also depended on something practiced long before the first stone ever fell. They turned preparedness into a public ritual. In the shadow of the Minoan palaces on Crete, the wide, open courtyards and unusually broad, straight corridors leading to the outskirts of the city were likely more than just grand architecture. They were the stage for a vital civic exercise, the community disaster drill. In a society intimately familiar with the tremors of the earth, reducing panic was a matter of life and death. Elders and officials would organize regular simulations where the entire population, from the youngest apprentice to the oldest priestess, would practice moving along these predetermined evacuation routes. The goal was to build muscle memory to make the correct response during a real earthquake as automatic as breathing. This was not a suggestion but a practiced, coordinated performance. The community learned to move as a single, calm entity toward designated safe zones outside the city walls, turning a potential stampede into an orderly procession. This principle of rehearsal extended far beyond earthquakes. Historical records from ancient China describe how military exercises frequently included disaster scenarios, such as simulating a breached river dike. Soldiers would practice building emergency barriers and evacuating civilian populations, seamlessly transitioning their battlefield discipline into a humanitarian mission. These large-scale reenactments served a dual purpose. They tested the physical infrastructure like the strength of a dam, while simultaneously training the human infrastructure of the city itself. The drills were followed by debriefings, where leaders and participants would discuss what worked and what needed refinement, creating a continuous feedback loop for improving their emergency plans. By normalizing these exercises, they transformed preparedness from an abstract fear into a tangible, communal skill. The chaos of a real disaster was met not with confusion, but with a deeply ingrained sense of what to do. So what would it take for a modern metropolis to embrace this ancient wisdom, to make neighborhood evacuation drills as routine as a fire alarm test in a school, building that same collective muscle memory so that when the ground shakes or the waters rise, every citizen knows their role in the dance of survival? This constant practice ensured they were ready for the expected, but their greatest strength may have been a willingness to rewrite the rules entirely when faced with the unprecedented. Every disaster was a brutal but effective teacher. When the dust settled and the floodwaters receded, ancient engineers did not simply rebuild what was lost. They became forensic scientists of failure, meticulously studying the rubble to understand exactly why one wall had crumbled while the one beside it remained standing. This process of post-disaster analysis was a disciplined cycle of continuous innovation, driven by empirical evidence rather than guesswork. They documented collapse patterns, noting which architectural forms had proven weakest. They collected survivor accounts, learning which escape routes had saved lives and which had become death traps. In the repeated rebuilding of cities like Lisbon after catastrophic earthquakes, this painstaking observation led directly to evolved architectural standards. Builders saw that rigid, heavy buildings often failed first, so new codes mandated more flexible, lighter structures. They noticed that narrow streets became tombs when buildings fell, so subsequent city plans featured wider, straighter thoroughfares for evacuation. This was a culture of humility and experimentation, where master builders openly acknowledged the limitations of their current knowledge and actively sought enhancements. Following a volcanic eruption, Roman engineers would analyze which of their concrete structures had held firm. They discovered that mixtures richer in specific types of volcanic ash, a material they called pozzolana, displayed even greater resistance to heat and shock. So they refined their recipes, incrementally improving the durability of their most vital material with each new disaster. They were treating catastrophic events as the most demanding laboratory tests imaginable, using the results to steadily advance their entire craft. How can our modern engineering industries, often bound by rigid codes and liability concerns, foster a similar cycle of fearless, evidence-based improvement? This relentless pursuit of betterment, this willingness to learn from broken stones, is what ultimately separated cities that vanished from those that endured for millennia. The ruins of these cities are not just monuments to the past, they are a living blueprint for our future. We have walked through the echoes of ancient streets, from the flexible foundations of Knossos to the water-harvesting cisterns of Petra, and seen a common thread. True resilience was never about brute force against nature, but about intelligent collaboration. It was found in the shock-absorbing joints of a Japanese home, the strategic voids of Tenochtitlan, and the shared knowledge of a community that could read the warnings in the sky. These engineers did not see a flood and dream of a taller wall. They dreamed of a smarter canal. They did not see an earthquake and pray for immovable stone. They built structures that knew how to dance. This profound synergy between human creativity and the raw power of the planet is their greatest legacy. It is a reminder that our own modern challenges, from rising seas to raging wildfires, are not necessarily new. They are simply asking us to remember a forgotten wisdom, to stop building fortresses and start building partners. The principles are all here, waiting in the dust. The flexible design, the redundant systems, the community-centered planning, they all point toward a future where our cities are not just places we live, but living, breathing ecosystems in their own right. So as you go about your day, look at the world around you. Look at the concrete, the glass, the way the water flows after a heavy rain. Ask yourself, how could my community bend without breaking? What ancient lesson could we relearn to build a safer, more sustainable world? This journey does not end here. If these ideas have sparked your curiosity, if you see the potential for a more resilient future, then share this knowledge. Please like this video, subscribe for more explorations into the mysteries of our past, and join the conversation in the comments below. Tell us how you would rebuild. Together, we can weave the enduring strength of the ancients into the fabric of tomorrow.